Okay, thank you very much for the invitation. It's very nice to be here. Actually, it would be better to be there. And so first thing to begin with, I want to wish happy birthday to both P and S. I'm not sure whether the title of the conference was chosen on purpose, but it fits. So happy birthday, Kobe and Sergey. I was lucky enough to see them recently in Cetraro. Let me, so this is a continuation. Well, first of all, this is joint work with Marcello Mamino and Pantelis Eleftheriou. Pantelli was virtually in Pisa for 1 year, so we worked on this project, and it's for us, for me at least, was a kind of continuation of an old project that I had with Marcello many years ago about orthogonality. So let's remind that if you have two definable sets in a given structure, are orthogonal if they do not interact, in the sense that the only definable sets in a Cartesian product of x and y, or powers of x and y, is just a finite union of boxes, namely of the form AI times B, A times B, where A is inside X and B is inside Y to some powers. So you cannot define anything interesting. There are no interesting relations between X and Y, only trivial ones, finite union of boxes. Of course, you can give us similar definitions for several orthogonal sets instead of two, but it turns out that pairwise orthogonality implies orthogonality. And for this, you need to allow Cartesian product, Cartesian powers in the definition. So the main example, the main source of orthogonality is the following. You just take two arbitrary structures, X and Y, and you put them together in a two-sorted structure, which we may call it disjoint union, M, X, disjoint union Y, which is, it's just a structure with a sort isomorphic to X, a sort isomorphic to Y, and with no relation symbols involving both sorts. So you have two non-interacting structures considered inside a single structure. So for instance, you can take two copies of the reals and make the disjoint union of them. So here it's important to notice that although the two sorts are isomorphic, of course, there are, by orthogonality, there are no definable bijections between the two sorts. So it's really two sorts of the reals non-interacting. So for instance, if you consider R1 times R2, the first sort, a product of the first and the second sort, or a product of the first sort with itself, they are both definable in this two-sorted structure, but the former has less structure than the second because there is no diagonal. So it's just something without, you cannot define the diagonal because you would need a definable bijection between the two. Okay, so the main question we want to address is the following, and I'll tell you that we are not able to answer it. So the question is, given a group definable in a disjoint union of two structures, what can we say? Well, the trivial example would be if you have just a group inside a single sort, or you may have a direct product of groups, one inside one sort and one inside the other sort. Or you may have slightly more general, a direct product modulo finite center, because a finite group is definable everywhere with parameters. So are there other examples? Well, there are. So a less trivial example is the following. Let's call it an irrational torus. So you take, again, two disjoint copies of the reals, but only additive reals with the order. And you can take a group which is just R times R, but the first copy of R times the second copy of R, modulo as discrete subgroup, which essentially is a lattice, and you can see a generator of the lattice in the picture. And you have to choose the parameters, and you choose the parameters of the lattice as in a suitable way. Okay, this group I claim is definable in the two-sorted structure, although the integers are not definable. So the lattice itself is not definable, but this group nevertheless is interpretable. Why is that so? Because you can take a big enough rectangle, like in the picture, containing a coset for each equivalence class modulo the lattice for each coset. And then you can define the group as the big rectangle, the dark rectangle, modulo a suitable equivalence relation. The important thing here is that the parameters cannot be chosen arbitrarily. In particular, the angle, so to speak, doesn't make sense to speak about the angles because these are living in different sorts. But the angle, in some sense, should be non-infinitesimal, because you need the fact that there are only finitely many points of the lattice inside the dark rectangle. Only in this way you can define the group, actually interpret the group as a quotient of the dark rectangle modulo a definable equivalence relation. Notice that these lines, the lines which are not horizontal or vertical cannot be defined because you are in these two sorted structures, but nevertheless, this group is definable. So it's a torus, abstractly it's a torus, but not, it's isomorphic to a torus, but not definably. The isomorphism cannot be definable because this group doesn't split definably if C and D are in generic position. Actually, you may arrange so that if C and D are irrational, this group will have no infinite proper definable subgroup. So in particular, doesn't split as a product. But nevertheless, is definable in this two-sorted structure. So there are non-trivial examples. Another non-trivial example, well, let me first give a definition. A definable set is internal to another one. U is internal to V if there is an N and a definable surjective map from V to the N to U. So internal is something similar to interpretable, no? Now, an observation is that if X and Y are orthogonal and you have a subset of X times Y, this subset can be internal to X if and only if its projection to Y is finite. So namely, you have X times Y, you can depict it as a rectangle, X-axis, Y-axis. To be X internal to means that you have finitely many horizontal lines, and Y internal, you have finitely many vertical lines. Just because by orthogonality, this is the situation. So if something is internal to both sorts, then must be finite. Okay, now the previous work on this, there are some previous papers to be quoted. One is Ruszowski, Peterson, and Pillay, who observed inside a much larger work, they observed that if you have a group definable in the reals, which we know it's a Lie group, the universal cover of it is definable in general is not definable in the reals, is only locally definable by results of Edmundo. But it will be definable in the disjoint union of the reals and the additive integers. This is because this locally definable cover will have a definable section. And then this definable section will induce you know that covers of groups in general are classified by so-called cocycles, which are maps from the quotient square to the kernel. And the cocycle classifying this particular cover here has finite image in the kernel. The kernel is essentially definable in the integers. And therefore, it's definable. It's definable in this two-sorted structure. Now, with Mamino, we proved a kind of converse. If you have a group definable in the two-sorted structure, then it must be a cover of a group definable in the reals. More precisely, there is a subgroup internal to the integers, this is the kernel, such that the quotient is internal to the reals. So it's exactly a converse of the previous result. And more generally, instead of the reals, you can take an arbitrary structure. Instead of the integers, you can take a superstable structure of finite Lasker rank and definable Lasker rank. And actually, Wagner generalized this, strengthened this further, and actually it's enough that X is arbitrary and Y is simple, a simple structure. So you have at least two examples, non-trivial examples of groups definable in two sorts. So the rational torus and these covers of groups. So then things become complicated. Can you classify these groups definable in two sorts? Now, there is a bold conjecture, which was inspired by an observation of Woody in Oberwolfach, is maybe this is that if X and Y are arbitrary structures, and you take a group definable in this two-sorted structure, then G is going to be generated by something internal to one sort and something internal to the other sort, something definable. And actually, more than that, not only generated, every element of the group is a product of an element of the first set and an element of the second set. I don't know if this is too bold. X and Y are just arbitrary structures, so this is, model theory, not even tame model theory. It's just model theory. And maybe it would be safer to say that G is abelian, but I don't know. I mean, I don't know any counterexample. And this is true in all the examples that I mentioned before. So in the universal cover or in the rational torus. So if the conjecture is true, then in the abelian case, you can obtain some structural consequences. In the abelian case, you would obtain that G can be obtained as a quotient of a locally definable group by a discrete kernel. In other words, you may take the definable group generated by A inside G, the group generated by A inside G, which is locally definable, countable union of definable sets. The group generated by B, this is again locally definable. You take the direct product. This group generated by A, despite the fact that it uses the operation of G, turns out that can be locally defined inside a single sort. And also B can be locally defined inside the other sort, up to isomorphism. And the kernel can be taken to be discrete in the sense that it intersects every definable set in a finite set. So it's exactly like the trivial example that I put at the beginning, namely direct product modulo finite kernel, except that here you have you have to go to the locally definable category, and then you have locally definable modulo, direct product of locally definable groups modulo a discrete rather than finite kernel. So this is the bold conjecture that we want to discuss. And we will see that it's true. I mean, the main result is that the main conjecture is true, if X and Y are ominimal. This raises interesting questions, for instance, about possible generalizations. Okay, now to discuss the conjecture, it's convenient to introduce a new notion, which is the notion of cohesive set. So a definable set is cohesive if, whenever you have two definable sets non-orthogonal to it, they are non-orthogonal to each other. So in some sense, cohesive means that it cannot be splitted. It's only one piece. It's something very connected. You cannot interact with one part of C without interacting with the whole of C. So if U interacts with C and V interacts with C, they cannot interact with different parts. They have to interact between each other. And there are some nice properties of cohesive sets. So in particular, it's unsplittable. So cohesive set, if it is internal to a disjoint union, so if X and Y are orthogonal, and this is internal to the union or the product, which is the same, then it's internal to one of the two. No, it cannot live in one part and in the other, in one part and the other part. If something is internal to a cohesive set, is itself cohesive. So all parts of a cohesive set are cohesive. And if U and V are cohesive and non-orthogonal between each other, then the product is cohesive. So once you have a cohesive set, you have a whole bunch of whole universe of cohesive sets. So you can take Cartesian products, subsets, and everything is cohesive. So most interesting structures are cohesive. For instance, we will see. But of course, the direct product of two groups living in different sorts is not cohesive. Now, the main well, there is a theorem that we can prove. The conjecture is still open, but a theorem we can prove is the following. If you have a group interpretable in the disjoint union of finitely many ominimal structures, so all the structures are ominimal and they are orthogonal, then you can prove if G has dimension 1, then it's cohesive. And in particular, it's internal to a single sort by properties of cohesive sets. In general, if G has not dimension 1, is not, of course, necessarily cohesive, can be a direct product. But there is a case such that there are cohesive subsets of G, such that G is a product of these cohesive sets. In particular, and each one of these cohesive sets, of course, it's internal to a single sort of this. So, moreover, these sets can be taken to be pairwise orthogonal, because if two of them are not orthogonal, you can replace them by the product of the two, and it remains cohesive. And this K,
Alessandro, can I ask something?
Yes.
The ominimal for you is arbitrary ominimal? Or
Ominimal, arbitrary, yes.
Okay.
These sets can be taken, you don't even need a group operation or anything. And these sets can be taken to be, don't need definable choice, nothing. These sets can be taken pairwise orthogonal. And in this case, K is uniquely determined. And we may call it the dimensionality of G. I chose the word dimensionality because Kobe, Udi, and Pillay in a paper spoke about unidimensional groups, and this is exactly what it is. One dimensionality means unidimensional. Unidimensional intervals. So it's a generalization of that. Okay, notice that these xi's appear in the hypothesis, but not in the conclusion, really. So this, the concatenation of these xi's can be regarded as a single minimal structure. You can concatenate two minimal structures just putting one after the other, separated by single points. So this can be really considered as a single minimal structure, although a pathological one because it cannot carry any group structure. So the hypothesis of the theorem can be just replaced by simply saying that G is interpretable in a non-minimal structure. So if G is interpretable in a non-minimal structure, which may consist in several orthogonal parts, then there are these cohesive sets. And if G is dimension 1, it's already cohesive. However, it's convenient to keep a version of the theorem with the xi's, with the sorts, because to prove the theorem, we have to pass through a weaker version of the theorem in which we don't mention cohesiveness. We just require that the sets Ci are not required to be cohesive, but just internal to a single sort. So of course, if they are cohesive, they are internal to single sorts. But you may have a weaker version in which you just have orthogonal sorts and you can find Ci's, maybe not cohesive, but each one internal to a single sort. So this is a weaker version of the theorem, but we have to pass through that. And notice that the weak version of the theorem is already sufficient to prove the bold conjecture in the minimal case. So if you have a group interpretable in two orthogonal sorts, minimal, then it's a product of two subsets, one internal to X and one internal to Y. So we are aiming towards the theorem. And I would like to, the proof of the theorem is a reduction to the case dimension 1, in which case the whole group is cohesive, and the case when the group is definably compact and abelian, in which case it's not necessarily cohesive, could be an irrational torus, for instance, which lives in two different sorts. So when the dimension is 1, the proof of cohesiveness depends on some minimality properties. So I don't know how to generalize this to other settings like geometric setting, or for instance. So the ingredients are, if you have a dimension 1 group, if you have a definable subset of it, the boundary is finite by minimality. Then another fact is that there are finitely many subsets of the group with a given boundary. So if you have a circle, for instance, you fix the boundary, there can be only two intervals, two sets with the given boundary, if you fix 2 points. And moreover, another property of one-dimensional groups, definable in a minimal structure, may consist of several orthogonal parts. So given two infinite definable subsets, you can move them, you can, by a group translation, so that they overlap in an infinite set. So these are all because in the one-dimensional case, infinite sets have interior, and of course, you can move them to have interior, so that the intersection
Alessandro?
is interior. Yes.
If you remove a point from the center, from the interior, then you can have many intervals where this point is removed from it.
And so what?
So all of them will have the same boundary. You say only finitely many definable sets with the given boundary.
Only finitely. So if you remove, well, by a boundary, I mean the closure minus the interior.
Yes.
So
you can just have many intervals with the same missing point in the middle.
Many intervals, but then this point is
no,
not...
and you remove one point from the center, from the interior. Remove 0. and you get a union of two intervals, bigger and bigger, and they all have 0. I don't, or just an interval. I don't understand what you mean. Maybe you say what you mean by finitely many definable sets with a given boundary.
But you are speaking about you are inside the reals, say. You remove the 0, you have an interval, but this interval, in the boundary of the interval, there is not only 0, there is also the boundary points of the interval, no? Right?
Disjoint
Disjoint what? Sorry, maybe I did something wrong here.
No, you're right. I think you're right. Sorry.
I'm right?
My mistake.
Okay. Well, then otherwise I don't go further. I mean, it's just wrong.
No, it's my mistake. Sorry.
Are you sure? Well, anyway, modulo this, I'm going to give a proof based on those ingredients that the group of dimension 1 is cohesive, interpretable minimal structure. Well, of course, if the minimal structure has a group operation, then the whole structure is cohesive, and everything definable in the minimal set is cohesive. So the interesting case is when the minimal structure is just consists of several sorts, right? So you have your group. You want to prove that it's cohesive. So according to the definition, this means that if you have two definable sets non-orthogonal to it, they are non-orthogonal to each other. Okay, so since A and the group are non-orthogonal, then it's easy to see that there must be some non-trivial relation between A and G. And it's easy to see that there is a definable relation, which is non-trivial, it's not a finite union of boxes, between A to the n and G to the 1. So this is small observation. You can take n and 1. Anyway, there is a non-trivial relation between the two, A and G. Now, this non-trivial relation defines a map, induces a map from the Cartesian from A to the n to the power set of G. So namely, you take a point here and you consider the points of G in relation with it. And since the relation you started with was non-trivial, this R tilde is as infinite image. But for each given input, A, small a, the boundary of R tilde A is finite, just because it's a definable set inside a one-dimensional group. So by minimality, there is a uniform bound on the size of the boundary. So we get, by ordering the points, a definable map from A to the n, from G to the k. Since there are finitely many possibilities for the set given the boundary, and since there are infinitely many possibilities for the set, it means that the image of this map is infinite. So there are infinitely many possible boundaries that you can code. So composing with a projection from G to tk to a suitable factor, you get a definable map from AN to G with infinite image. Similarly, you get the same with the other sort B. You get another map from B to the L to G with infinite image. By a group translation, these two images can be made to overlap in an infinite set. So you may assume that F and G have the same image. And now you can define a non-trivial relationship between the two sorts. You just say X is in relation to Y if F of X equals G of Y. And this cannot be a finite union of boxes, this relation. So witnesses the non-orthogonality of the two sorts. So in some sense, the group has all parts strongly interacting. And out of it, you prove that it's not cohesive. Okay. So now this is a bit disappointing because if M is a non-minimal expansion of a group, every definable set is cohesive. So this cohesiveness is not an interesting notion outside of the many sorted context. Just because M itself is has a one-dimensional group structure, so M itself is cohesive. Cartesian products of cohesive sets is cohesive. Something internal to a cohesive set is cohesive. So once you have a non-minimal structure which expands a group, everything is cohesive inside that structure. But then now let's go back to the many sorted situation. In the many sorted situation, so if you have an arbitrary minimal structure, which may consist in concatenation of several orthogonal sorts, what can happen? If you have a simple, definably simple group, then by Petersil-Pillay-Starchenko, we know that G is internal to a real closed field definable in the structure. But the real closed field is cohesive, so the group is cohesive. So simple groups are cohesive. So one-dimensional groups are cohesive. Simple groups are cohesive. By the way, question for the people. Can you show that a definably simple group in an NIP structure is cohesive? I don't know. So this is, it's a, maybe these notions, I don't know how interesting they are, but they raise maybe interesting questions. So one needs to understand better simple groups in other contexts. Okay, so we have now dealt with dimension one and simple. Let's consider now definably compact abelian groups. They need not be cohesive. There is the irrational torus or simply a direct product of groups living in different sorts. So, but at least we want to prove that they can be generated by finitely many cohesive subsets. Let's see if we can do that. Definably compact abelian. Okay, so we have a definably compact abelian group in a non-minimal structure, which may consist in several sorts. For simplicity, suppose that the domain is just included, rather than simply interpretable, in x times y, where x and y are orthogonal. So it's x and y, you depict it as it's a rectangle, say, and the group is there, the domain is there. So the domain must be a finite union of subrectangles. And we want to prove that G is a product of two sets, A consisting in finitely many horizontal lines, and G consisting in finitely many vertical lines. Of course, if the group is a direct product, you can just take one single horizontal line, one single vertical line, if it's just a direct product. So this is what you want to prove. Okay, the sketch is the following. First of all, the group operation, since x and y are orthogonal, the group operation cannot be very complicated. Actually, you may have any definable function rather than the group operation. For any definable function, you have that piecewise, there is a finite partition such that on each piece, this operation can be defined separately on the x and the y sort. This is just a simple consequence of orthogonality. Namely, there are definable maps, mx and y, such that for each AB in a given piece of the partition, the x coordinate of the product is an operation depending only on the x coordinate of the factors of the multiplying of A and B, and similarly for the y coordinate. So this, you just use the definability of the operation, not the fact that it's a group operation. So of course, if this set D of the partition is the whole group, this simply means that the group is a direct product. And so you are done. This piece of the partition, however, may be small, but not too small, because at least one of them, since the group is definably compact, at least one of them is rather big, is generic. Because we know that the union of two sets is generic, one of the two is generic. That means finitely many translates cover G times G, generic in G times G, this D. So we may take one of these D's is generic. So now, if we manage to write a generic set as A times B, then by finitely many translations, you may do the same for the whole group. So it's enough to prove this kind of decomposition G equal AB for a generic subset. So take a generic subset. This is a generic subset of G times G. But then you can easily show, using the properties of generic sets, that there is a generic set, there are two generic sets in G rather than G times G, such that U times V is contained in D. So each generic set in G times G contains product of generic sets in D, in G. Now this U and V can be are generic, so you can show that there is a group translation such that the intersection is, you can move them in such a way that the intersection is again generic in G. So you have this Q. So now this Q is generic in G. But now remember that G is included in X times Y, so it's a finite union of rectangles in X and Y. So one of these rectangles must be generic. So Q contains a generic box, Qx times Qy, one living inside X and the other living inside Y. And you are almost done. So you essentially can take A and B to be Qx and Qy or something very related to it, modulo some translations. So now it's not difficult to see that to find A and B as desired. So it's going through a process of further refinements of generic sets. So you have boxes inside generic sets, boxes in two different senses, one in the sense of G times G and the other. So this is essentially the case of definably compact abelian groups. Now, remember that we are aiming towards the weak theorem, in which there is no notion of cohesiveness. We just have several sorts, and we want to generate the group by sets living inside a single sort. So if this weak version of the theorem holds for a subgroup and a quotient, then it holds also for the group, you can show. We have already managed to deal with dimension 1 and definably compact. Dimension 1 because they are cohesive, definably compact because of what I just proved. And so now, by Petersil-Steiner, every definable abelian in a new-minima structure is either definably compact or contains a definably subgroup of dimension 1. So by induction, you have the theorem, the weak theorem for all definable abelian groups by induction. So we have the simple case and the abelian case of the weak version of the theorem. But now again, by induction, once you have the abelian case and the simple case by induction based on group extensions, based on the first line of the slide, you can prove it for all definable groups. So this is the weak version without the cohesiveness property. Now let's go. So let's go now to the last slide. So far, we have been slightly cheating because we ignore the difference between definable groups and interpretable groups. In particular, when I proved the definably compact case, I assumed for simplicity that your group was inside X times Y. was inside a product of two orthogonal sets, in general may simply be interpretable in the disjoint union, but not inside a product. So it doesn't make sense to speak about horizontal lines, vertical lines, which is something which is used in the proof in the definably compact case. But this can be handled through the results of Eleftherio, Pedersen, and Ramakrishnan, which says that interpretable groups in a minimal structure are definable. And moreover, they can be definably embedded, not as groups, but just as sets, in a Cartesian product of one-dimensional definable group intervals. Okay, now I'm aiming towards the strong version of the theorem. I have a group living inside several sorts or minimal sorts. I want to produce finitely many cohesive sets such that the group is a product of the cohesive subsets. So far, I only obtained that subsets which are internal to a single sort, but not necessarily cohesive. Okay, now these one-dimensional group intervals need not be pairwise orthogonal. However, if there are two of them which are not orthogonal, you can replace the two of them with the product of them, and you get something cohesive of dimension 2, and then you keep going until you get this corollary that every definable group in a nominal structure can be embedded in a Cartesian product of finitely many pairwise orthogonal, because if you keep going, when you cannot go further, it means that the pieces that you are left are orthogonal. So if they are non-orthogonal, you take the product and remains cohesive. You do this as long as you can. When you cannot do it further, it means that you are left with orthogonal cohesive sets of various dimensions. So we have reduced to a situation in which we can apply the hypothesis of the theorem in the definably compact case. We started with assuming that the group was inside the product of cohesive orthogonal sets. So we can reach this situation through this corollary. Moreover, we can now prove the strong version of the theorem. Why? Because the weak version allows us to write G as a product of definable subsets, not necessarily cohesive, but internal to a single sort, each one. But the corollary allows to reduce to a situation in which the sorts are cohesive, and something internal to a cohesive is again cohesive. So we have obtained the full strong theorem. So any group is a product of cohesive subsets. And there is a difference between the weak version. So this is the last slide, so I have essentially finished, but let me say just one more word. So the weak version is certainly not true in general for arbitrary structures. The weak version could be. So because there is no reason, the weak version, essentially the strong version says that any group has finite dimensionality. So it can be written as a product of finitely many cohesive sets. This is the dimensionality. There is no reason in general why a group in some arbitrary structure has finite dimensionality. So it could live in infinitely many different sorts. So you can take just infinite direct products in a suitable structure with a suitable structure. It's not entirely trivial to cook up an actual example, but there is no absolutely reason this is true. While the weak version of the theorem, namely the bold conjecture, could be true for much more general structures, if not arbitrary structures. So it could be true that if you have a group living in finitely many different sorts, it's a product of subsets, each one living in a single sort. But this is wide open as far as I know. Okay, I have finished.